let us begin.
I'm ready.
Candidate, welcome. We will bypass the pleasantries. You are applying for a senior design position where the cost of failure is astronomical. I am looking to assess your theoretical foundation against the harsh realities of the field.
Understood.
Let us start at the macro level, examining the external structural integrity of our vessels before we move inside. What are the engineering criteria for determining the quantity, spacing, and structural sizing of column vortex shedding stiffener rings, often called aerodynamic spoilers, on ultra-tall columns?
Well, the primary mechanism we have to address is that ultra-tall, slender columns are exceptionally vulnerable to wind-induced crosswind oscillations.
The von Karman effect.
Yes, the von Karman vortex street. When a fluid, like wind, flows past a cylindrical column, it creates alternating low-pressure vortices on the downwind side.
Right.
And when the frequency of this alternating vortex shedding aligns precisely with the fundamental natural frequency of the column itself, well, structural resonance occurs.
Which we obviously want to avoid.
Exactly. To mitigate the resulting fatigue risk, we install structural vortex stiffener rings on the upper portion of the shell.
For the sake of clarity, I want you to visualize that failure mechanism before we discuss the mitigation. What exactly does a von Karman vortex street look like in physical terms?
Consider a flagpole in a strong wind. The flag doesn't just blow straight out, right? It snaps violently from side to side.
Okay, I follow.
That snapping is caused by alternating vortices peeling off the pole and creating oscillating low-pressure zones that physically pull the flag. Now, you scale that flagpole up to a massive steel column.
A much heavier flag.
Exactly. If the wind pulls it back and forth at the exact rhythm it naturally wants to sway, those deflections multiply. The metal fatigues, and ultimately the structure fails.
I understand the physics. But how are you quantifying this risk during the design phase? Walk me through the dimensional analysis conceptually. Do not just recite the formula.
We evaluate the risk using the Strawell number and critical velocity.
Right.
The Strawell number is a dimensionless constant. It's approximately 0.2 for cylinders. And it mathematically relates the frequency of vortex shedding to the wind speed and the column's outer diameter.
So it scales with the geometry.
Yes. Using that constant, we can calculate the critical velocity. This is the exact wind speed at which the shedding frequency matches the column's natural frequency.
And if that aligns with typical weather?
Well, if that critical wind speed sits below the maximum regional design wind speed for the plant site, then vortex spoilers are strictly mandatory.
Let us assume your analysis dictates that spoilers are necessary. I have seen junior engineers recommend wrapping the entire column in spoilers from top to bottom just to be safe. Defend the specific geometry of your implementation. Why do we not just wrap the whole vessel and eliminate the risk entirely?
Well, wrapping the entire vessel is frankly a severe failure in structural weight trade-offs. It demonstrates a lack of engineering intuition.
How so?
Because while helical strakes suppress crosswind vortex resonance, they dramatically increase the column's drag coefficient for inline wind loads.
Ah, I see.
Yeah, if you wrap the whole column, you effectively turn a smooth cylinder into a highly textured sail. The structural engineer must then update the static wind profile to account for this massive drag penalty.
Which requires more material at the bottom.
Exactly. It mandates a thicker shell at the base and adds immense, completely unnecessary load to the foundation.
Then what are the exact industrial parameters you implement to protect the column without turning it into a sail?
We adhere to standard industrial specifications, such as those governed by Bechtel or Floor. The geometry mandates a 3-start helical strake design.
Our start, okay.
Yes. These strakes must project outward by approximately 10% of the nominal shell diameter, and they wrap around the column with a pitch of 5 to 6 times the diameter.
And their placement along the height?
We strictly install them only along the top 33% to 50% of the column's height.
Why only there?
Because this upper boundary is where wind velocities are the highest, and the column's modal deflection curve exhibits the greatest structural flexibility.
Explain the physical mechanism behind a 3-start helical design. Why 3 distinct ribs?
Well, a 3-start helical geometry ensures that no matter which direction the wind blows, it encounters a constantly changing profile.
So it breaks the rhythm.
Precisely. It effectively converts synchronized rhythmic crosswind forces into randomized, disorganized turbulence. It breaks up the organized vortex street without unnecessarily maximizing the drag profile.
So it's a structural compromise.
In short, yes. It protects a tall column from resonant vibrations while managing the static inline wind loads at the base.
Theory is fine, but I want a quantitative example from the field. Give me a project metric where this was successfully applied to save structure.
Certainly. We analyzed a slender 65-meter xylene fractionation column on a recent project. The structural analysis yielded a very low natural frequency of 0.45 hertz.
That is quite low,
It is, and our calculations revealed a critical wind velocity of only 12 meters per second.
which is an everyday breeze.
Exactly, that is a completely common wind speed at the plant site, meaning the column would vibrate constantly. So, to counteract this, the engineering team specified a 3-start helical strake system exclusively for the top 22 meters of the column.
And the result?
This intervention completely eliminated the risk of vortex resonance during daily operations without requiring a massive, expensive foundation upgrade.
Since you brought up field implementation, I want an example of a real-world field failure trap here. Give me a scenario where the theoretical calculations on the drafting table were perfect, but the actual fabrication process resulted in millions of dollars wasted.
The most common and devastating trap occurs when fabrication teams weld the helical strakes directly to the column shell plate, but neglect to factor in the thickness of the external thermal insulation.
They bury the strakes.
Yes. If the strakes don't project far enough past the outer insulation cladding, they're entirely buried beneath the insulation during final assembly.
Making them useless.
Completely useless aerodynamically. You've spent the capital expenditure to fabricate and weld them, but they leave the column entirely unprotected against wind vibration.
And what is your detailed metallurgical caution regarding the welding of those strakes? Wind loading implies constant dynamic stress.
The welding protocol must be flawless. Helical strakes must be attached using continuous fillet welds.
Not stitch welds.
Exactly. Some fabricators try to save time by using intermittent stitch welding. That is a critical error. Intermittent welds create structural notches and moisture traps behind the strakes.
And under dynamic load, that's a disaster.
Under continuous wind loading, those notches act as stress concentrators, initiating localized thermal fatigue cracking. Furthermore, the trapped moisture leads to severe corrosion under insulation, or CUI, on the highly stressed upper shell.
Very well. We have successfully secured the external shell against the environment. Now, let us step inside. A column that survives the wind must still function internally under severe pressure variations.
Naturally.
I want to test your architectural logic on process internals. Moving to our next question. What structural load combinations and deflection limits must a static engineer use to verify a distillation column's internal tray support rings per process licensor specifications?
The operational load vector for a tray support ring is a combination of 3 primary downward forces. First, the mechanical dead weight of the stainless steel tray panels themselves.
Okay.
Second, the weight of the downcomer liquid volume, the actual fluid holdup sitting on the tray deck. And finally, we must factor in the nominal operational vapor pressure drop across the tray deck.
Which pushes up or down.
Right, which pushes upward or downward depending on the flow dynamics.
That accounts for perfectly steady state operating conditions, but industrial chemical processes are almost never perfectly steady. What happens when the system surges?
Well, then we apply upset and explosive surge multipliers.
Explain.
During process upsets, such as a sudden water slug hitting hot hydrocarbons or a rapid steam release, the internals experience violent upward or downward pressure surges.
And the licensors have specs for this.
Yes. Process licensors, such as UOP or Axons, mandate that the internal support rings must withstand a transient design load multiplier of 7 kilopascals to 14 kilopascals. That's roughly 1 to 2 psi of differential pressure.
A massive shock.
It is. The rings must absorb this sudden surge without undergoing any permanent plastic deformation.
Let me challenge your understanding of tolerances with an analogy. Balancing optimal vapor-liquid contact on a distillation tray is like trying to balance a full tray of water on a bowing table. If the table sags even a few millimeters in the center...
The water rushes away from the edges.
Exactly.
The edges run dry, the vapor shoots straight up the dry side, and your separation efficiency plummets. What are the exact deflection limits required to maintain separation integrity under these surge multipliers?
Your analogy precisely captures the mechanism of vapor-liquid bypassing. To maintain an even liquid level across the entire tray deck and prevent fluid from bypassing the downcomers, the maximum allowable elastic deflection for major structural support beams is strictly limited.
To what dimension?
It is capped at a ratio of L divided by 800, or a maximum absolute deflection of less than or equal to 3 millimeters. 3 millimeters? And how do you account for material degradation? The internal rings are subject to the same corrosive environment as the shell, yet they are significantly thinner.
The structural thickness calculation must mandate a double corrosion allowance applied to both faces of the support ring.
Why double?
This is critical because the support ring is welded directly to the interior column wall. It cannot be easily unbolted and replaced during standard maintenance.
So it has to survive the whole life cycle.
Right. The double allowance ensures the structural rigidity remains within that 3 mm tolerance over the vessel's entire design life.
Give me another field trap. I want a scenario where standard engineering oversight leads to the catastrophic collapse of these internal trays.
A critical failure point frequently occurs during plant maintenance, specifically during a chemical turnaround wash.
How so?
The trap is specifying standard lightweight tray support rings based entirely on vapor-liquid operational loads, but failing to calculate the static liquid load during that turnaround wash.
Ah, because they fill it with water.
Exactly. If maintenance crews fill the column entirely with water to wash it, the specific gravity and sheer static weight of that water can instantly overload the unreinforced tray structures, causing a cascading internal collapse.
Distill the requirement of these components into a core engineering mandate.
Tray support rings must act as rigid structural constraints inside a column, maintaining strict leveling tolerances under process pressure surges to ensure efficient vapor-liquid contact.
Provide a quantitative example of how you engineered around a failed deflection check on a recent project.
We evaluated a 4-meter diameter vacuum tower utilizing multi-pass distillation trays.
Okay.
The central support beam carried an exceptionally heavy liquid load, and our initial calculations showed a deflection of 7.5 millimeters under upset conditions.
More than double your 3 mm limit.
Well beyond the limit, yes. It would have ruined the process efficiency. Rather than thickening the entire beam, our solution was to weld vertical stiffening plates to the beam, geometrically increasing its moment of inertia.
Did that bring it into spec?
It did. This critical modification reduced the deflection to 2.2 millimeters, safely meeting the licensor's specification.
I'm looking for a detailed metallurgical caution here. Distillation columns often utilize clad materials for economic corrosion resistance, a cheaper backing steel with a thin layer of high-grade alloy. How does this complicate the welding of your tray support rings?
Significantly. When welding tray support rings to clad or lined column shells, for example, a carbon steel plate clad with Monel or 410S stainless steel, the support ring must be welded using highly compatible alloy filler metals.
And if they use standard materials?
If a fabricator carelessly attempts to weld directly through the clad layer using standard carbon steel consumables, it immediately contaminates the weld pool with iron from the backing plate.
Iron dilution.
Yes. This iron dilution causes rapid weld embrittlement and cracking, leading to the complete structural failure of the internal trays under pressure.
We will ratchet up the intensity for this final segment. We are leaving standard distillation behind and entering extreme environments. High temperature, high pressure, extreme load. We are talking about hydrocracking.
Okay, let's do it.
Another question. What structural mechanics and ASME Section 8 Division 1 design criteria govern the calculation of a heavy-duty catalyst bed support grid in a high-pressure hydrocracking reactor?
But the load scale in a hydrocracking reactor is, frankly, immense. The downward design force combines the weight of multiple catalyst layers, which frequently exceed 100 tons, along with the weight of the ceramic support balls, the operational liquid holdup, and the design pressure drop pushing down across the bed.
A pressure drop that isn't static, correct?
Correct. Crucially, that pressure drop increases over time due to catalyst fouling. We treat this massive total load mathematically as a uniform pressure load acting on a flat circular plate supported around its perimeter.
You mentioned ASME Section 8 Division 1. Do not recite the raw mathematics, but explain the conceptual analytical linkage for sizing this grid under that code.
The thickness of an unstayed flat catalyst grid is evaluated using a modified version of the UG34 formula for flatheads.
Conceptually speaking.
Conceptually, the code dictates that the required thickness of the grid must scale exponentially with the combined catalyst and fluid pressure load. But crucially, it factors in how the elevated operating temperatures severely sap the material's allowable stress. It must balance the physical pressure pushing down against the heat, actively weakening the steel.
This is where I must apply extreme pressure to your logic. You just gave me a static calculation, but hydrocracking is a dynamic, degrading environment. These reactors do not operate at room temperature. How exactly do you account for material yielding over years of operation under 100 tons of load at extreme heat?
You are targeting high temperature creep and relaxation.
I am.
This is the defining constraint of hydrocracking equipment. These reactors operate at sustained temperatures between 380 degrees Celsius and 450 degrees Celsius. At these temperatures, the steel grid is highly susceptible to continuous creep deformation.
Give me a physical analogy for creep so we understand the exact behavior of the metal over time.
Think of a thick piece of warm taffy suspended between 2 points.
Okay, taffy.
Even if you don't push down on it, over hours and days, it will slowly stretch and sag under its own weight simply because of the heat. Steel behaves the exact same way at 450 degrees over a period of years.
It just slowly sags.
Yes. The structural beams cannot merely be sized for initial yield strength. They must be sized using time-dependent allowable stress values from ASME Section 2, Part D. This mandates calculating for long-term creep strain across an unrelenting 100,000-hour design life.
And what are the strict deflection limits before this high-temperature creep compromises the process flow?
Static engineering specifications cap the maximum allowable deflection at the diameter divided by 1,000, or an absolute maximum of less than or equal to 2 millimeters.
2 millimeters of deflection on a 100-ton load at 450 degrees Celsius. Defend that tolerance. Explain the process consequences if you relax that limit and allow 5 millimeters of deflection.
Well, if the support grid deflects even 5 millimeters, it creates a physical slope. The catalyst pellets shift toward the center of the sagging bed.
Moving downhill.
Exactly. This movement causes uneven flow distribution, channeling the high-pressure fluids through the thinner edges. This channeling subjects the localized catalyst to incredibly high friction forces, violently pulverizing the expensive pellets into fine dust.
Which goes where?
That dust immediately plugs the bed. This spikes the pressure drop and forces an emergency, multi-million-dollar plant shutdown.
What is the ultimate failure scenario here? When manufacturing simplicity and cost-cutting override engineering rigor, what is the trap?
The trap is fabricating a catalyst support grid using unreinforced flat plates, simply to reduce manufacturing complexity and save fabrication costs.
And underload.
Under real-world 100-ton catalyst loads and high operating temperatures, these unreinforced plates will inevitably succumb to high-temperature creep. They will bypass the 2-millimeter limit, leading to catastrophic channeling, complete catalyst bypassing, and a highly dangerous premature plant shutdown.
State the core engineering function of this grid in a single axiom.
Catalyst support grids act as high-strength structural platforms that must resist both short-term plastic bending and long-term creep deformation to maintain uniform process flow through the bed.
Provide your final quantitative example for this assessment.
During the design of a diesel hydrotreater containing a 5-meter diameter catalyst bed, the initial fabricator design utilized a series of standard flat stainless steel bars.
Which was insufficient.
Extremely. Our time-dependent creep calculations demonstrated that the center deflection would reach 8 millimeters under foul conditions at end-of-run pressure drops.
Way past the 2-millimeter limit.
Yes. The static engineering solution was to add a massive, deep central structural girder to support the individual grid segments. This critical modification reduced the deflection to 1.5 millimeters, satisfying the strict 2-millimeter maximum specification and saving the reactor from future failure.
I require one last detailed caution. The internal grid does not exist in a vacuum. It must physically interface with the column wall. What is the critical failure point at that specific junction?
The perimeter sealing system. Where the grid joins the column wall ring, it must be designed with a highly reliable seal, typically utilizing bolted alloy hold-down bars and specialized high-temperature gaskets.
And the tolerances?
The tolerances here are entirely unforgiving. If thermal expansion differentials or improper installation opens a gap as small as 2 millimeters at this perimeter, the high-pressure fluid will bypass the bed entirely, seeking the path of least resistance.
Missing the catalyst.
Entirely. The fluids will flow right past the 100-ton catalyst bed, rendering the entire reactor process completely ineffective.
The interview is concluded. You have effectively defended your design basis against real-world constraints. All right, we are going to break character now. I want to step out of the interview and address you, the listener, directly.
We're going to look at an entirely new ecosystem designed specifically for working professionals to help you master those high-pressure moments. Okay, picture this. You're sitting right across the table from a panel of... They aren't asking about your hobbies anymore. They're dropping you directly into the hot seat to test your true operational readiness. Imagine you're in that interview. The pressure's on.
You're facing intense, high-stakes scenarios. In a real-world interview, you need something that prepares you for the absolute reality of the industry, where your split-second engineering decisions have massive financial and, of course, safety implications.
And that brings us to this absolutely game-changing app, which is available right now on the Play Store. What we're looking at here isn't just some random list of questions thrown together. No way. It is an exhaustively structured solution. It provides AI-driven, highly practical, example-based Q&As that form a comprehensive framework. Because the sheer scale of this architecture is massive. We're talking about a structure spanning over 200 sections, and it caters to everyone, beginners, intermediate folks, all the way up to experienced and expert professionals. The rule of thumb here is simple. If it's in the plant, it is in this app. It really acts as a complete pedagogical roadmap for your entire career. Now, you might be wondering, how does it deliver all this content without getting super repetitive? Well, the core of this app is what they call the Studio Engine. It's this AI powerhouse that entirely eliminates the limitation of predetermined static questions. Instead, it dynamically generates a highly structured, unlimited repository of practical Q&As right when you need them. So by doing this, it actually tailors a dynamic mock interview simulator specifically to your current knowledge gaps. It brilliantly illustrates how concepts are queued sequentially. You just select your domain, your section, and then your concept, and the app continuously feeds you the next logical scenario. Because getting a question is one thing. Understanding the multidimensional answer is a whole other ballgame. The system doesn't just feed you a wall of text. Every single generated response is deconstructed into 5 distinct steps. It actively highlights the critical responses you absolutely must deliver and warns you of the hidden pitfalls. Now, they represent only a minor part of the unlimited Q&As available in the app, but they serve a very specific, crucial purpose. They perfectly simulate real-world office arguments, differing viewpoints, and intense technical debates. Because let's face it, engineering isn't just taking a test in a vacuum, right? It's about navigating heated arguments and proving your technical acumen when challenged by your peers or your superiors.
And a massive part of these sessions is the power of roleplay. After every mock interview section, videos feature AI-generated live roleplay interview sessions complete with feedback on pertinent domain subjects. Giving real roleplay interviews after enriched technical discussions acts like an incredible catalyst. It is a tremendous confidence booster for any aspiring candidate, consolidating everything you've learned into practical, real-world readiness. Which leaves us with one final, very important thought. What step are you going to take right now to engineer your own success? Mastering your craft is a lifelong pursuit, and with tools like this at your fingertips, the depth of your knowledge truly has no limits. I highly encourage you to check out this combined integration of texts, text-to-speech audio, videos, and live role-play interview sessions. The tools are definitely out there to unlock your potential. The only question is, are you ready to use them?